Hi, everyone. Thanks for coming in person. Hello, everyone on the Zoom. Uh, this is, as you all know, this is the CIIR Talk Series, and we are pleased to host Alane Suhr from University of California, Berkeley. Alane recently joined Berkeley as an assistant professor. Before that, uh, Alane was a PhD student at Cornell and later a postdoc, or better to say, a young investigator at AI2, at Allen Institute for Artificial Intelligence. The lab is focusing on building language using systems that communicate with and learn from human users in collaborative situated interactions. So interactions between agents and humans and AI systems. And the talk today is also related to this area, which I'm personally very excited to hear more about it. Interactive language agents, training, evaluation, interface. Without further ado, please welcome Alane virtually to UMass.
Well, yeah, thank you for the for the intro and also for the invitation to speak. So today I'm going to talk about three different sort of perspectives on interactive language agents, focusing on how we can train these models, how we should be evaluating them, and what interface we should be giving to them. Oops. Just adjusting my slides. Okay, all right. So I wanted that today, the talk is going to focus on interactive language agents. For me, this is defined as agents that use language to do things in the world, for example, by following instructions in some kind of situated environment. So like I said, I'm going to focus on three different sort of pillars of this question on developing interactive language agents, including how can we continually train these models and improve them through interaction with their users, as opposed to just pre-training them ahead of time and then running inference when they're actually deployed. And how can we evaluate these models at scale on new tasks and new domains that we maybe don't have the right benchmarks for yet. And then finally, talking about model interface design, why is robustness of these models and predictability of their behavior a really critical feature of system design, and how could we evaluate this in a model? So a lot of my work centers around collaborative interactions, so I wanted to more abstractly talk about this to start with. When I talk about what I mean when I say collaborative interaction. So in this setting, we have two agents. They are operating in a shared world, and they're acting towards a common goal, and they coordinate their behavior by using natural language. So we have two different core natural language problems that we can study in this setting. First, language understanding, where we want our system to map from a user's utterance and maybe a current world state, like its observations of the current world, as well as the interactions history, like previous utterances and actions, to a new set of actions that execute an instruction, or maybe they answer a question or something like this. We also are able to study the problem of language generation, where the system itself has some goal in mind. Maybe it's a goal that's shared with the human collaborator, a current world state, as well as the interactions history, and we want to generate an utterance that's sent to the user. So one unique aspect of these collaborative scenarios is that both of the agents can act in the world simultaneously or in turn, but critically, they can both influence the state of the world. So this supports a lot of really interesting dynamics that we don't see in single agent or like single turn interactions. For example, we have the ability to dynamically delegate tasks. So if our user says, can you take the pliers, and the system runs away to the corner of the room, this is obviously not great, but the user can decide instead that they're just going to do it themselves and maybe issue a simpler instruction to the system. So this is just one form of adaptation within interaction that supports continual learning. Continual learning is very core to natural language use. We use explicit and implicit feedback from the people that we're talking to drive our own language learning. So for example, if I start talking about something and it seems that the person I'm talking to doesn't understand a particular concept that I've mentioned, then maybe I'm going to rephrase it in a way that is more understandable. But we also expect our interlocutors, the people that we're engaging with, to adapt their language use via feedback. So again, if I kind of like look confused maybe, then I'm expecting my partner to, explain something more in depth. And the key insight here is that if we build systems that can transform these very natural feedback cues that arise in interaction into actual learning signals that allow our models to adapt over time, then we'll actually both better support collaboration because we will be reacting appropriately to the behavior or to the feedback our users are giving during interaction. But we'll also be able to learn more efficiently because we'll be sort of making the most of all the interactions that are coming from our users. So there's different kinds of feedback that we could take into account and learn from. First, including explicit feedback. For example, if our user issues the instruction, hold this for a second, and then the system does this and it gets some positive reward. But if it then runs away with the pliers, then it gets some negative reward. And this is particularly relevant to like modern approaches to training models with human feedback. So for example, preference-based learning that you see in sort of the RLHF style paradigm. But we can also learn from implicit feedback that arises in an interaction. So let's say that our system has some goal for the user to bring it a hammer, but it incorrectly generates this expression, bring me a saw. Now the user who's going to try to cooperate with our agent will bring a saw to the agent because they're going to follow the instruction, but the agent will realize that this is actually not the goal that it wanted to achieve. And so we can construct a learning signal that both includes the fact that this was an incorrect description of the intent of bringing a hammer, but that it actually might better align with what the user actually did, which was to bring it a saw. So we actually can learn two different things from this single interaction. So in general, in this collaborative interaction scenario, we are looking at two agents that are acting in a shared world towards a common goal and use natural language to coordinate. So we can understand problems like, or we can study problems like language understanding and generation, dynamic delegation, continual learning, and through different kinds of feedback that arise in interaction. And this is a really general setting. I usually study these situated environments where you have some instructions and then a set of actions that you can actually navigate in the world around. But you can also consider this collaborative interaction much more generally for any system that is interacting in multiple turns with like a human user. Okay, so to sort of set the stage for talking about continual learning, which is the first sort of pillar that I'm going to talk about today, I wanted to discuss Serial Bar, which is this environment that I built several years ago for studying collaborative language-based interactions. So this is a situated and collaborative environment that is sort of based around sequential natural language instructions. The environment has two agents acting in a shared world with different props to refer to and navigate around, as well as different terrains and different cards with different colors and shapes on them. And there are two agents that are collaborating together in this environment, a leader and a follower. Abstractly speaking, the leader is responsible for sort of doing the high-level planning towards their shared goal, and then describing what the follower should do through a natural language instruction. And then the follower's responsibility is just to follow these instructions to the best of their ability. Now, their shared goal is to pick up matching sets of cards. In our case, a matching set is 3 cards with unique color, shape, and count across the 3 cards. So in this particular game board, maybe we'll get the 2 pink stripe card, the 3 red triangle card, and the 1 orange square card. And if we were to select all these cards at the same time, we would have a valid set and we would earn a point. And we want to maximize our score, so we want to collect as many sets as possible. We designed this scenario to really target language use as the way that these two agents are coordinating. So in order to actually succeed at this task, the leader has to write instructions for the follower, and the follower has to follow these instructions to the best of their ability. And we designed multiple additional mechanisms that further encourage collaboration in the environment. So we have this observability gap where the leader can see a top-down view of the game board so they can see everything going on. but the follower only has a first-person view. So this discourages the follower from sort of doing whatever they would like towards some goal because they don't actually know all the information about the environment, so they might do something that messes up the leader's plan. But it also encourages leaders to write instructions that are actually grounded with respect to the follower's current perception of the environment. So for example, if I want my follower in blue here to get the 3 red triangle card, I'm going to have to tell it to turn around because you can see in the bottom right, it doesn't actually see that card right now. We also have a capability gap where the follower can move farther per turn than the leader. And this just encourages the leader to actually coordinate with the follower, because if they just told the follower to stay put the whole time, they're not going to be able to pick up very many sets. And it also encourages the leader to give more complex instructions to the follower because they have more steps to use. So I'm just going to give a quick demo of this game so you have a sense of like what's going on. Okay, so the first thing I'm going to do as the leader is I'm going to pick up the 2 pink stripe card, and then I'm going to write 2 instructions for my follower to pick up the 3 red triangles and the 1 orange square like we talked about before. So I'm going to say turn around and get the red triangles next to the mountain, and then get the orange card. Okay. And the model that's actually going to be executing these instructions is a model that we trained through continual learning with human feedback. So as you can see, its turn began, the system is turning around, it's recognizing that there's the red triangles, it's picking up that card. But oh no, I didn't realize that if on the bottom right here, you can see in their view, there's another orange card that I didn't realize was there. And this is an orange triangle card. But we just picked up some triangles, so that's why these cards are outlined in red, because now we have an invalid set. We have 2 cards with triangles on them. So I made a mistake as the leader, but I can fix this by issuing new instructions. Because we're in this multi-turn interaction, we have this ability to recover from our errors through the flexibility of interaction and language. So I'm going to write 2 more instructions: deselect the card you are standing on and turn left and get the orange square past the windmill. Okay, so I'm going to end my turn again. I'm not going to move anymore because I don't really need to, and we'll see if our model can recover. So here the model has deselected the orange card. That's good. And also made sure that the red triangles are still selected and is now turning sort of around and going past this windmill. And then gets the orange square, and we've earned a point for the set that we picked up. Okay, cool. All right, so that was just a brief intro to serial bar, where we have these 2 agents, a leader and follower, acting in this shared world towards their goal of picking up sets of cards, and they use instructions to coordinate with each other. So we can study different language problems here, like language generation in the form of instruction generation and understanding in the form of instruction following. We have nice aspects of dynamic delegation. You saw that when I mistakenly was too ambiguous in my get the orange card instruction, the model was able to recover when I issued it another instruction in the next turn. And there's different ways that we could actually learn from this interaction to further improve the model's performance. So for example, I could provide explicit feedback as I watch the model like navigating the environment to tell it basically which actions were good and which were not good. That's actually the kind of feedback that that model I was just interacting with was trained on. But we can also consider types of implicit feedback. So I got some implicit feedback during that interaction where because my goal was for the agent to get the orange square, but my instruction was too vague. I just said get the orange card. It picked up the orange triangle instead. So now I've learned probably I need to be a bit more specific in my instructions going forward. Okay, so I'm going to talk about 2 different types of instruction following the 2 different types of feedback that I just described that we explored in this domain. So the first is training our model to be better at following instructions through interactions with human users. The general setup here is that during interaction, we're going to get binary feedback from our users as they observe the model executing their instructions. Our approach is to basically cast these feedback signals as bandit signals that we then can use to update our model with contextual bandit. So what does this feedback mechanism actually look like? During instruction execution, the leader can give feedback either through the interface buttons or through their keyboard. They give positive or negative feedback basically at any time as the agent is moving. And that means that it's like super intuitive to give. It's not disruptive to the interaction because they're taking turns anyway. So just to illustrate this a little bit, let's say as the leader, I said, move forward and slightly to your right until you see a card with 2 black squares, pick it up. And then my follower starts their turn and they start moving towards the orange, sort of towards the black squares. So I give it some good feedback, but now it's gotten a little too close and is now facing the orange stars. So I'm going to give it some negative feedback. But then it sort of diverts, avoids this orange star card and heads towards the target card. And then at the very end, once it's selected the correct card, it gets a positive feedback. So the kind of data that we're learning from here is for every action that our follower executes, we get the world state in which it was executed, the original instruction that I had issued, the action that was executed, as well as the probability of that action according to the policy that was deployed, as well as binary feedback that I'm providing as the leader. And so we want to cast this as a contextual bandit problem where we want to maximize the immediate reward, or also here is the feedback for each action. So again, we have this world state, instruction, action, sampling probability, and binary feedback. Our objective is to maximize immediate reward, which forms a contextual bandit problem. The gradient here is the feedback f times the gradient of log probability according to the current policy parameters, which actually introduces a bit of a problem for us when we're working in an offline setting with negative feedback. For positive examples, this is actually not a problem because f equals 1, and so our gradient looks like supervised learning gradient just on data that got positive feedback instead of superhuman demonstrations of instruction following. But for negative examples, what we see is that as we train on these examples, their probability goes to 0, which is great because we don't want to sample these kind of actions. But then the gradient of this, but the problem is that the log of that becomes close to negative infinity, and then the negative examples will start to dominate the loss. So what we do instead is add this coefficient, which is a clipped inverse propensity score, which is why we need the original sampling probability according to the policy that was deployed. So this allows us to overcome the issue of loss exploding by training on negative examples. So the general learning setup here is that we're going to initialize our model with some supervised data. So this is human demonstrations of human written instructions. And we're experimenting with the sort of minimal amount of demonstration data that we need to start with a decent enough policy such that when we deploy it the first time with human users, it is good enough that we're going to get some meaningful feedback. Like, in other words, the model's not just going to completely fail. During deployment, we will sample actions from the current model parameters, here indicated by theta r, where r indicates the current round of training and deployment. So we will sample some actions conditioned on every new user instruction, collect this across a number of interactions, get some feedback from users in real time as the agent is executing instructions, and use this to construct a training data set that we're going to use after each round to retrain our model with contextual bandit and then redeploy for the next round. So the main results from this study is across 11 rounds of training and deployment with around 250 to 350 interactions each. We start with an instruction completion accuracy of around 66, 67%. But we see that over time, across 11 rounds, we get this up to like 82% accuracy, which is really great. Our model has learned something, or at least user instruction the instruction execution is better. We also see that the score of the game has improved as well from 3.3 to 5.3 points, which is showing that this process of continual learning is not just locally improving, but it's actually supporting better interactions with their users. But one question that might arise, and this is actually a very general question that I think that we need to keep in mind as we're building systems that are changing alongside users, is this improvement actually coming from the policy improving, or is it coming from the users adapting? So each round here, the score from each round is coming from a subset of the instructions that people actually issued during that round. So the sort of test set at each X point here is actually different because we're sampling from things that people like asked for in each round individually, which leaves the opportunity for these improvements to come from users issuing different instructions. So people are going to adapt, to the system during interaction to make it more useful for themselves. For example, they might simplify their instructions. So one of the questions is, what's the contribution of training on human agent interaction data versus users adapting to a system? So how we evaluated this is we took the very first model parameters, the ones that are trained only on the demonstration data, where we got like 66.7% instruction execution accuracy. And then we deployed that same set of parameters at the very end, where the only difference is that the humans have adapted to the model. And we do see a significant improvement to like 70.4% instruction execution accuracy at the very end. And when we look at how the user instructions have changed, we find that, for example, they stop issuing instructions that ask for like more than one card, and mostly only ask for a single card per instruction. So they've sort of simplified their instructions in different ways. But the majority of this improvement from 67-ish to 82% accuracy is coming from the policy actually improving. We also looked at continual learning for improving an instruction generation model. And the general idea here is we want to learn how to generate language by observing how it affects the world when it is when it is given to a person. So in this particular setting, we're going to generate instructions, observe how users execute them, and then compare the system's intent to what the user actually did to get a bandit learning signal. So given a current world state, we're going to use a deterministic planner to figure out what the plan or the intent should be. For example, for the human here, the ideal situation, or the human follower here, the ideal thing they could do is take this yellow path here and then get the 3 blue circle card. And then we're going to take this deterministically generated plan and pass it to a neural network that will allow us to sample an instruction. So for example, turn right and go straight past the lake and collect the 3 blue circle card. So when we deploy this model alongside people in interactions, we will have this initial world state, which is this, this image basically at the top right here. We will have the system's generated plan that's coming from the deterministic planner, the instruction that was sampled from our neural network, as well as the human's execution of that instruction as they were a follower following the instruction. And this has the same data type as the system plan. They're basically just sequences of like the locations that the agent visited and the cards that it picked up. We'll also ask users after each instruction whether the instruction was correct with respect to what they actually did and whether it was grammatical. Now, the main insight here is that we can learn from this by comparing the system's original plan to what the user actually did. And if these two diverge too much, then we can say that the instruction's not actually describing the original plan very well. But regardless, it could still be a good description of what the user did, even if it's unrelated to what the original intent was. So once we have all this data, we will first filter out things that, or give a negative reward to things that are either incorrect with respect to what the user did or ungrammatical. And if neither of these two things are true, regardless of whether the plan actually is similar to the execution, we're going to create a positive example pairing the execution with the instruction that was sampled, because the execution here is reflecting the instruction meaning. Because we have a user who is taking the instruction and turning it into an execution. If we heuristically identify that the plan is equivalent to the user's execution, then we can say the instruction does accurately communicate the plan, and so we get a positive reward for that. So for our training data, we have access to the world state, a pose sequence, which is either coming from the system plan or the execution, an instruction, and a binary reward. And then again, this creates a contextual bandit learning scenario. So we have a similar setup here where we are training the model initially with some supervised data, and then we are deploying and training it in rounds. Here we looked at 14 different rounds of deployment and training. And we see that over time, the rate of task completion accuracy, which is the rate at which humans are actually doing the thing that the system intended for them to do, goes from like 45 to 79% accuracy. So the so the model itself is continually improving in its ability to generate instructions that relay its intent accurately. Okay, so to summarize this scenario, we're talking about continual learning by iteratively adapting model parameters and deploying our model in real time with users, where we can acquire some kind of feedback, either implicit or explicit feedback, basically into a bandit learning signal, which is really nice for training because it's relatively stable and ends up looking a lot like supervised learning. But another note here is that when we think about these dynamic settings, we should take into account not just how our model is updating, but how our users are adapting to the system as well. So we have these sort of second order dynamics where we can't be too sure if our model has actually improved at the task when the users are now expecting new tasks from our system. Okay. So now I want to move on to talking about evaluation of these kind of models more generally, especially when we don't have these sort of fixed settings like serial bar to evaluate them in. So we have explored this from the setting of digital agents, where the task of a model here is to also follow instructions or ask questions by executing instructions in a situated environment. Here we're looking at these digital environments, for example, web navigation, where we might issue an instruction, tell me the cost of my latest canceled order, get some kind of language model-based agent like GPT-4 or GPT-4V, or maybe a human to go and execute a couple of actions, for example, clicking on my orders, and then give us an answer here. Other tasks in this domain include things like device control. So for example, if I ask which reminders did I recently check off, then the model has to go in, open the reminders, open the history or something like that, and then give me a response at the end. So there's been a lot of progress and attention to this direction in the last several years, but these models are not very good. They still make a lot of mistakes. So one big question here is how can we evaluate the performance of these models at scale and across domains? This is especially important for autonomous agents that we are just letting run sort of wild on the internet, for example, to do your shopping for you or whatever. We still want to be able to understand how well these models are doing when we are deploying them. We also ask this additional question of, could we actually additionally improve these models by having access to a general purpose evaluation function? So existing evaluations of these kind of systems fall into two main kinds of categories, including simulation-based benchmarks, where we have an executable environment and user instructions paired with handcrafted test cases, where we can take an instruction, sample some actions from our agent, and then for whatever sequence of actions it's sampled, test them against these test cases and get some kind of result on whether or not it actually completed the instruction. We also have demonstration-based benchmarks where we have user instructions paired with human demonstrations of those instructions being followed. And we can use reference-based metrics to compare the human's demonstration to what the system actually did. But one of the issues with these is that we can't arbitrarily evaluate new trajectories very easily because we have only one reference. So instead, we ask the question, could we actually just generally evaluate an agent without these kind of test cases and without demonstrations? So the goal of creating such an evaluator would be to take, the instruction, some instruction X, as well as a sequence, an agent's sequence of actions execution, and then map this to some kind of evaluation, whether it was successful or not. So we propose two different main approaches to this. One is an end-to-end approach, where we just take these two inputs as well as a prompt, did the agent successfully complete the task, pass this to some kind of vision language model like GPT-4V, and then determine whether or not it was successfully executed. Oops. But we also evaluate another approach where we sort of decompose this problem of reasoning about what was actually done by the agent during its trajectory and what the intent actually was. So for example, we would first here try to caption this trajectory with, your favorite VLM without taking the instruction into account. So we get some kind of dense caption of the screenshots, for example, that it observed when it was executing the instruction. And then we pass this caption and the original intent, as well as the sort of prompt of like, did the agent successfully complete the task, to your favorite text-only model. One of the benefits of this more modular approach is that it can be cheaper than the end-to-end approach. It can be more interpretable because you can identify if the error is coming from the trajectory captioning or not, and it can be ran locally or at scale if all of the components are open weight. But one big challenge here is, okay, we propose some evaluators, but do they actually accurately evaluate our system? So we want to see whether they are accurate across different agents themselves, agent policies, and across different domains. We also want to explore the problem of whether we can actually use these evaluators to improve our policies autonomously, especially in completely new domains that they were not trained on. So we explore a couple different benchmarks, simulation-based benchmarks like WebArena, where we have, again, our Oracle metric is a hand-designed test case, as well as demonstration-based benchmarks like Android in the wild, where we have human demonstrations of instruction execution. And the Oracle metric here that we want to compare against is human annotation, where we actually personally have to go in and do qualitative analysis of whether an instruction was correctly executed by our agent or not. We also introduce a new domain of iOS device control, where we have new instructions, but a new environment for agent instruction execution. And in this completely new domain, we don't actually have any Oracle metrics. Of course, in practice, we are going to do evaluation and make sure that it works compared to like human judgments. But this is simulating the setting where we don't have any sort of Oracle evaluation metric. So we look at a number of different policies. For WebArena, the state of the art at the time was the GPT-4 text-only model, where it takes as input in the HTML tree of a web page. For the Android in the wild setting, which is, again, this Android device control setting, we're going to compare against some state-of-the-art models, as well as the human demonstrations that were provided with the data set, because we want to make sure that our evaluator works both for poor policies as well as like good policies that we know should be good, like the human demonstrations. So in terms of the evaluators, like I mentioned before, we have both these end-to-end approaches like GPT-4v, as well as some modular approaches. For example, captioner plus a captioner model plus a mixtural LM. These are completely open weight, which allows us to run it locally pretty easily, as well as a captioner plus GPT-4 model, where all we've done is replaced the LM to be GPT-4. So when we evaluate across a bunch of different policies and different evaluators, as well as the different benchmarks, we see that we have overall relatively high accuracy for our evaluators when compared with the Oracle evaluation metrics. But there are some errors that the model makes. For example, it's not that great to be at modeling long contexts, so like long trajectories, and can sometimes have incorrect reasoning, but correct evaluations at the very end. Our analysis also showed some pitfalls of reference-based metrics. So the standard evaluation metric for Android in the wild is this action matching score. So given a human demonstration, we're going to feed in some prefix of the gold standard demonstration, ask our model, what action would you take next? And then ask like, what proportion of actions would the model predict correctly given this gold standard prefix? The state of the art on this metric is currently like 71%. And for just comparison, we have another evaluation showing that the large version of the auto UI model is better than the base version, according to this metric. So we ask the question whether we actually make the same conclusions with our evaluation that's actually based off of task completion instead of individually predicting whether each action is correct. So here I'm just showing the actual evaluated success rate according to a number of different evaluators, including our own human judgments, and then the 3 different styles of evaluators that I talked about before. across 4 different agents, including auto UI base and large, cog agent, and human agents, which are the demonstrations that people provided in the actual data set. The first thing to highlight here is that we found that only like less than 2/3 of the human demonstrations, which are used as references for these models for evaluation in this data set, are successful, which is not great because we would like ideally for 100% of the human demonstrations to be accurate. So this is troubling. We also find that our metrics, including the human judgments of success, show that the base model for auto UI is actually outperforming the large model in terms of success rate for following instructions accurately. And overall, we just find that looking at something like success rate is much further from takes us much further from actually building these useful digital agents that actually successfully follow instructions compared to the numbers that the metrics based off of references give us. So as I showed in the previous couple slides, these reference-based metrics are telling us, we're having like 70% accuracy or around that, but success rates are less than like 20%. Okay, so we also looked at how we could autonomously improve these models through the use of these evaluators that we proposed. So we looked at 2 different approaches. First, improving these models at inference time using reflection, and also at fine-tuning time by using behavior cloning. So the setup here is that we're going to study inference time adaptation on the WebArena dataset and filtered behavior cloning to see if we can transfer a model to our completely new iOS domain. So here I'm showing the success rate of the GPT-4 agent, which is the state-of-the-art on WebArena, where the state-of-the-art here is like 15.6% success rate. The blue dashed line is okay, so actually I'm just going to explain reflection first. So in reflection, basically what you do is you sample from your model. You have some metric that tells you whether or not the sample was correct or not. If it was incorrect, you prompt the model again to say that was wrong, try again. You get a new trajectory and you can evaluate it again. So you can do this in multiple rounds. So again, the black dashed line at the bottom here is just showing the sort of baseline success rate of the GPT-4 based agent without trying again. In the blue dashed line, this is sort of the upper bound of the reflection approach, where the evaluator that is telling us whether samples are correct or not is coming from the Oracle metrics from the WebArena dataset. And then the other 3 lines are where we're using the metrics that are coming from our actual evaluators that we're proposing. And you can see, of course, it's not going to reach all the way up to the Oracle evaluator performance over time because we're not judging all of the trajectories as correctly, but we do see significant improvements over time, even with our open weight models. So we can see an up to 29% relative improvement over state-of-the-art using an automatic evaluator. And what's really notable about this is we don't actually need any test cases, any gold standard demonstrations, or anything like this to improve this model. We just need a couple of prompts for our model, for our evaluator model, and then we can just run it, and then at inference time we improve. Our other approach is to use behavior cloning, where we start with some base model that is fine-tuned specifically for the sort of device navigation, device control task. And we will train the model on a number of tasks. So for example, we have like 80 different training tasks that we define for our target domain. We get our initial model to sample about 9 trajectories per task, and then we get success judgments from our model on whether or not each action that was executed actually moves us towards success for that task. And then once we have that judgment, we can fine-tune only on the state action pairs that give us positive feedback for this, like that are judged as correct. So the result here is that the baseline model is successful on about 8 of the 52 tasks. where when we just sample all the actions and we train on all of them, we get a slightly improved performance to 11 tasks. And then when we actually use filtered BC, so we're only going to train on the actions that got us closer to our goal, using just our automatic evaluators, then we can improve up to 14 tasks. Okay, so to summarize this scenario, talking about evaluation, we show that we can use autonomous evaluators that take as input traces of an agent's interaction with an environment in order to autonomously evaluate these models at scale and in new domains. And we can use both inference time and fine-tuning approaches to continually improve our model by getting feedback from these autonomous evaluators. Okay, so for the last section, I wanted to talk about sort of our expectations of these models and how we are using them in practice. So the main question I want to pose here is, how consistently do models actually understand language? People are using today, the sensitivity of models to different prompt features as a way to improve performance in the models. So you can look at things like, RL prompt or other sorts of prompt engineering based things that find all the tiny little nuanced changes you can make in your prompt to get better performance. So this is maybe a feature of these models, is the ability to tune them very carefully to maximize performance on some end task. But there's been not very much work trying to characterize this kind of sensitivity, especially to features that intuitively shouldn't actually influence a model's performance in practice. So one issue that we identified is that a lot of the time, if we want to evaluate a model's performance, we're going to pick maybe one or two prompts and then just sort of roll with them. We're not going to identify what about our choices in that design actually made it work or not work for that task that we were evaluating. So there is some additional work that's looked at other spurious features beyond the ones that I'll talk about today. For example, if you're providing few-shot examples, how robust are the models to the order of those examples in context? Okay, so what we're exploring here is the variance of these models across different prompt formats. So for example, if we have a task where we have some kind of passage and then we need to answer something about it, we could reformat this task by modifying different spacing or different capitalization or things like this. And none of these changes should really influence the performance of the model because they don't change the underlying semantics of the task. Yet we do see a huge range of performance across these different formats. This is actually a real task on detecting stereotyping, where you have some input passage and the task is to identify whether it includes stereotyping in the passage. And so the sensitivity of these models is actually quite troubling here because if we're going to use this downstream, we want to make sure that our system is actually accurate. So there's a couple places where not paying attention to this sensitivity is a problem. So if we want to make conclusions about relative performance of different models, when we just choose a single prompt format, we're maybe not taking into account how the format might be different for a different model. We might see that users are experiencing much lower performance than what developers report if they choose a different model. And researchers might be reporting properties of models that don't really exist consistently, like, for example, a lack of bias or different cognitive capabilities. So a lot of the time when people report things, they'll report either the prompt that they happen to choose. Maybe they will try to optimize the performance to find the best prompt that gives you the optimal behavior on your task. Or maybe we should be reporting the minimum performance, which is like, how bad does the model get with a reasonable prompt for a particular task? So we introduce a framework for evaluating sensitivity of models to prompt design. We want to make sure that when we're evaluating these models, we only choose prompts that are actually plausible. And also ones that are just semantically equivalent to one another. So we define a grammar for each task in our evaluation. Given a sample format coming from a real prompt engineer, we define a grammar, and we have the space of options are like the casing of the items, separators that we use, multiple choice labels, etc. These options are inspired by examples of real prompts that people had written. So this is an example of one of the grammars where we have 3 different inputs. And so you can see that we have like options like what are the different item formatting? Do we want to use capital letters? Do we want to use lowercase letters, numbers, etc.? The main headliner sort of evaluation or conclusion from this work is that there is huge amount of spread between these models across different prompts. So here, this is averaged across 53 different classification tasks. Each point here is a different task. And we're showing the spread across prompt formats for different models. Here, we had just sampled like 10 formats from our grammar, but I will also describe a way that we can do better sampling of formats to get an even better lower bound on the spread. And we find that the spread and sensitivity here remains high, even when we are increasing the number of few-shot examples, when we're looking at instruction-tuned models, and when we're increasing model sizes. So one issue here is that we might make assumptions or conclusions about the relative performance of different models given a particular prompt. So let's say that we know that given one format that we chose, that Llama 277 billion is better than Falcon 7 billion by 2 percentage points. We want to see what's the probability that there exists a second format where we actually see the opposite result, i.e. they reverse the trend, where the second format is semantically equivalent to the first one. We see this is actually like true like 14% of the time for 14% of these other semantically equivalent prompts. And in 47% of these alternative prompts, both of the experiments here, both using prompt 1 and then the other prompt, were actually significantly different in reporting like the accuracy. So this 2% accuracy difference is actually significantly different. And this is not good. This is basically showing that like we can make one significant conclusion with a single random prompt that we chose, but if we modify that prompt slightly, we might actually make a significantly different conclusion. And we see similar results comparing different model sizes. So one issue here is like if we were able to sample from the grammar completely and try to evaluate on the full data set, this is super expensive. We could do like a local search where we basically start with a single prompt and then we want to like modify it minimally to sort of traverse the graph, traverse the grammar under the assumption that these changes are actually like correlated with one another. But we find that actually they're not. We don't see that there's any continuity in performance or predictability of performance given another prompt that's like similar in the string space. So what we propose instead is, given our limited inference budget, which is the number of times that we can evaluate a prompt on some task instance, we still want a reliable lower bound on this spread. So what we'll do is instead allocate inferences with prompt formats using Thompson sampling. And we find that comparing naive sampling, upper confidence bound sampling, and Thompson sampling, we can get closer to the actual true spread with lower inference budgets with Thompson sampling. And the other thing is that our approach format spread actually produces a lower bound on the prompt format spread. So it's actually possible that the actual spread of a particular model for a particular task is much higher than its results suggest. Because our approach allows us to do more efficient estimation of this spread, we can also evaluate the models on more expensive. We can also evaluate more expensive models like GPT 3.5, where we also find significant performance spread up to like 55% spread for a number of tasks, for this task on the very right here. All right, so just to conclude, today, I've been talking about these interactive language agents, as well as questions around how we can continually train and improve these agents through interaction with human users, how we can evaluate them automatically and improve their performance at scale without requiring human annotations. And then finally, how we should be thinking about the robustness of these models and whether the predictability of their behavior given their inputs, is a critical feature of system design. Okay, so I wanted to leave time for some questions, but just also wanted to say thank you for attending. The work on web agents was presented at Column 2024 a couple of weeks ago, led by my PhD student Xiaoyi Pan. A lot of the serial bar work was conducted by a bunch of cool people at Cornell, including my PhD advisor Yoav and Claudia Yan, who did a lot of the really initial environment development. And then the format spread work was presented at CIIR this year, led by Melanie Sklar, who's a PhD student at UW. Okay, happy to take any questions.
Thank you so much. Very interesting talk. So we have about 7 to 8 minutes for question answers. Any questions from the audience here or folks online? So while people are thinking about their questions, I found this prompt kind of the diversity of outcomes for different prompts quite interesting, and it's kind of reminded me of these query refinements we had in the search engines in the past, that different reformulations of the same query led to different result lists and quite different performances. And it's similar in this case. And I assume that also other NLP applications with the same, like maybe if you look at the machine translation literature, probably similar things could have happened if we use paraphrase of one language and look at the translation. I'm just wondering, what are the solutions that the other natural language processing applications have been looking at? Because this sampling seems very reasonable to me, but also expensive, as you mentioned. So maybe a more cost-effective, cost-efficient solution would be desired.
So is the solution, so are you looking for a solution to the estimation problem or a solution to the instability problem?
Stability problem, basically having a robust evaluation across models.
Yeah. Well, I mean, I think that we sort of are trying to propose, our intent is to propose an efficient way of doing this evaluation. One of our initial assumptions was that the space of the grammar would be like locally coherent. That turned out like not to be true. Models have a lot of idiosyncrasies and like how they're actually evaluating, or like how they're actually like responding to different inputs. So it's really unpredictable, like what the accuracy would actually be given a particular prompt format. So I guess my answer would be that like our format spread approach is, I mean, I don't know if it's like the optimal search, but it's certainly more optimal than like doing it's more optimal than doing an exhaustive search, certainly, and because it gives a lower bound, I think that it's just important to not use it as a way to like prove that a model is robust, but more as a way to diagnose that a model is fragile, if that makes sense.
Yeah, that makes a lot of sense. But it's a quite important and interesting topic. So I'll pass the mic. So there's a question here, Julia.
Hi, thanks for an interesting talk. I'm just wondering, for the format spread, like, did you look at or have any thoughts on if you trained a model specifically for this? Because I know some instruction tuning data sets kind of consider different ways of formatting the same prompt. So do you think that could address some of these problems?
Yeah, I think that like one option could be to like identify if there is a format that like just generally works better for the model and have some kind of like rewrite preprocessing that always like rewrites something in that format. One of the problems that we identified, though, is that even with a particular model, there's not much consistency in which format is best for all tasks. So like we couldn't find a format that like worked better for all tasks. There were one or two features I think we identified that like always tanked the performance of a particular model, but there was nothing that was like clearly going to work for all of the tasks, if that makes sense. So that's one option. I guess you could also consider a setting that's like more ensemble based, where you try a couple of different formats and then, you do some kind of like majority voting to see if that would work across different prompts, which of the prompts is better. Or which, across the different prompts, do you have some consistent answer that's coming from them despite this variance? You could consider fine-tuning the model with, the prompts that are sampled from our grammar. I feel like this is sort of glossing over the instabilities in some way. It's sort of identifying, okay, here's a particular instability, but that we can identify, that we can like fine-tune out, but who knows what other kind of like instabilities or unpredictable like behaviors there are. Yeah. I think in practice, if you want a model that does really well at a target task, and you know what the task is, and you're able to evaluate it, having robustness to different ways of formulating that task is not as crucial as it is to just have a function that gives you good performance on your task. So I remember when I was first working on this, a bunch of students were concerned that like this is something that we would need to run for like every possible use of a prompt. But in practice, like if you're prompting a model because you want it to give you some high accuracy on a task that you're going to use like downstream for something else, then I think it's totally fine to use something that's like not robust, if that makes sense.
Thank you. Is there any other questions?
I think there's a question on Zoom.
Hi, Alane.
Hello.
Thanks. Very wonderful talk. So I have maybe a couple questions. Hopefully they're quick. So one, in terms of the spread, have you considered looking at comparison to humans and how well the spread is, like, do humans have, presumably humans will have some sort of a spread with different formats. It probably is smaller, but have you considered looking at that and comparing?
So we didn't do this, I think, because we had the assumption that for most of the decisions, like there wouldn't be like a significant difference with people. I think it is fair to there's some other recent work, I think, in different domains that is sort of also making this assumption that people are not that people are like always going to be good at a particular task or something, and that's not actually the case necessarily, because we have like different priming effects and stuff like that. We didn't run this, and we probably are not going to. I guess the assumption would be that like even if there is variance in human performance, it's not going to go from like 85 to 5%
Yeah,
for a particular task,
sure.
which is really what the main like problem is that we were concerned about.
Yeah. And in terms of the serial bar, have you considered looking at generalization such that can you enhance the generalization performance of language modeling by learning in a grounded environment? So for example, let's imagine spatial analogies. There are lots of spatial analogies that humans make in everyday speech, and in text format, there isn't anything to ground the spatial analogies. But I wonder if, like, for example, you could have something where an agent learns spatial analogies in an environment and then generalize, or things like that, where you can improve language modeling outside of an embodied environment by learning in an embodied environment.
Yeah, I think this is a really cool question. I think like at scale, something like a spatial analogy is like, I think even for humans is not interpreted as spatial. I think analogies are interesting because I don't think that when we learn an analogy, we necessarily are grounding it. Because I think we learn a lot of like routine idioms to some extent that just sort of have the meaning that they're used for. So I think a lot of like figurative language and stuff like that actually doesn't necessarily require grounding, because I don't think that humans necessarily require grounding for it. The requirement of grounding is coming from maybe the first time someone proposes the analogy, right? So to invent an analogy or to invent some new figurative language, I think you probably do need to be grounded in whatever it is that you're building on top of. So maybe that's one case where I think like you probably do want to have grounding. But I don't, maybe this is like a too broad of a statement, but I also don't think that models are very good at like proposing new types of language use. And so maybe this is something that could help with that, but I think that's actually coming from a different problem, which is that they're not really trained to use language to sort of change how the world is working. They're more responsive or reactive type agents. Yeah.
Okay, thank you very much.
Thank you so much. There are still a few questions, but I asked them to be postponed to the one-on-one meetings. So let's thank Alane one last time.
Thank you.
Thanks for the very interesting talk. And